Hello, and thank you for joining us today. Our webinar topic is microwave extraction for mercury and beverages with quantitation by CVAA. Our presenter today is Jeff Forsberg, Technical Product Manager for Teledyne Leeman Labs. If you have any questions, please submit them throughout the presentation using the question function, and Jeff will follow up with you after the webinar. This webinar is being recorded and will be available within a few days. Okay, now I'm going to turn it over to our presenter, Jeff Forsberg.
Hi, everybody. I'd like to start out with just expressing my thanks for everybody attending today's webinar on mercury in beverages with the microwave extraction and the QuickTrace M7600 as our analytical technique. So mercury, inorganic or methyl mercury, is important to have monitored for potential uptake in humans. If we quantitate it, the contamination in our food sources, we can reduce that risk of exposure, and it can be adequately assessed. The World Health Organization states that both inorganic and organic mercury have toxic effects, which we all know. It's toxic to the nervous, digestive, and immune systems, threat to fetal and early childhood development, resulting in impaired neurological development in humans. So if we quantitate both species, either organic or inorganic, in food samples, that's going to be a valuable resource tool. By knowing the contamination, we're able to prevent harmful exposure, and that's going to minimize bioaccumulation effect, and that can potentially cross the blood-brain barrier. So this presentation, we're going to discuss a novel microwave extraction technique coupled with cold vapor atomic absorption, using the QuickTrace M7600 for total mercury determination in some selected beverages. So a little bit about the background. We were approached by our sales team in Korea to look at mercury in beverages. One of the reasons we were asked to tackle this task was there's a lack of methodology, or appears there's a lack of methodology outside of ICP mass spectrometry. I also did a search and I couldn't find a lot of applicable methods for CVAA. So what we wanted to do was microwave digest with detection by cold vapor atomic absorption. And then that also gives us the ability to potentially lower some of the detection limits in the beverage analysis for mercury. So the 7600, this is a cold vapor atomic absorption system. The dynamic range is 5 ppt, 0.005 to 700 micrograms per liter. It's got a center post design for the gas liquid separator. Typical reducing agent is 10% stannous chloride and 7% hydrochloric acid. The carrier gas flows to the GLS through the reference cell. So this is a dual beam system. So the carrier gas comes in through the reference cell, flows out of the reference cell, and goes over to the gas liquid separator. From there, the mercury's already been reduced to elemental mercury. It's going to be swept out, and it goes to the Nafion dryer and then to the sample cell for detection at the incident light of 253.652. So what affects the dynamic range of a continuous flow system? Well, typically, there's 3 easy steps for changing a dynamic range. High gas flows are going to equal short residence times. That's going to give you speedy results, but it's also going to decrease the sensitivity. Low flows are going to give you long residence times. It's going to increases the sample time, but it increases the sensitivity. Pump rates, you can increase or decrease the pump flow or the liquid flow to the GLS, that's your mercury load, and then time in sample. This is going to be the time that the probe is pulling the sample out of the sample tube and sending it off to the instrument for ultimate detection. So you adjust all three of those, or one or two of them, and you can achieve the desired dynamic range and results that you would like for your methodology. The laboratory apparatus needed for this experiment, 50 ml polypropylene capped sample tubes, 21 position sample racks, disposable single-use plastic transfer pipettes, and air displacement pipettes. I used a 10, 5, and a 1 mil pipette, 100 mil polypropylene graduated cylinders, laboratory microwave, of course, is essential. In this case, I used the CEM Mars 6, but you can use that and or similar type microwaves. Vessel capping station or a hand capping torque device. Digestion vessel cleaning brush, 100 mil volumetric flask, 10 to 20. I believe I used about 15. A large volume volumetric flask such as a 2 liter, 2,000 milliliter, funnels, DI water, wash squirt bottles, balance for checking pipette volume accuracy. So preparation for the system, I started out with prepping the 55 mil Mars Express digestion vessels, double rinse the vessel plug cap with DI water. I prepared a 10% Contrex cleaning solution. This is acidic cleaner and detergent, volume. You can use a similar cleaning type solution. Acidic phosphate free liquid detergent will work for descaling, mineral removal, and also oxide removal. I wet the microwave cleaning brush with 10% Contrex solution and clean inside the vessel. I used a CEM brush, part number is 302030, and then triple rinse the vessel plug, and vessel cap with DI water after you've gave the inside a good brushing with the cleaning brush. The next step is to add 10 mils of 10% nitric acid, volume to the vessel, and then number and label vessel plug, and vessel cap, so you can keep control and track which vessel performs within the microwave system for contamination and so forth. So you can go back and look at contamination for individual results. And also you can track your microwave digestion of your samples this way as well. Note that the maximum volume is 55 mils for the CEM vessel. 55 mil CEM vessel is 25 mils. That's the max volume. Cap and place the vessel in the microwave turntable in accordance to any manufacturer's load instructions. The CEM load instructions for 10 vessels, which what I'm using is 1, 3, 5, 7, 8, 9, 11, 13, 15, and 16, and here's depicted here in loaded into the turntable. And here is how I've set up the microwave vessels and labeled each every part of that microwave vessel. Load that carousel onto the microwave, put it in the cavity, ensure that it's correctly placed on the turntable drive lug, and then you want to set up a vessel cleaning method. For the Mars CEM Mars 6, I chose sample type is water, power 1000 watts, ramp time of 10 minutes, hold time of 10 minutes. My temperature, I ran it up to 180 degrees C, and I used a temp guard at 200 C. So if it goes above that 200 for any one of the vessels, it will shut down the program. And then you go ahead and run that cleaning method. And then while that's happening, you need to clean up some of the other apparatus for this experiment or your digestion. So you want a double rinse flask that you're going to be using, your 100 ml flask with DI water, your large 2,000 milliliter flask. So add 10 to 20 mils of 10% nitric, swirl, soak, and swirl again. Triple rinse with DI water. Funnel preparation, so I soaked the funnels in 10% Contrex. And then rinsed with copious amounts of DI water. What's really important is once this is all kind of set up, you want to perform a digestion apparatus baseline assessment. So with that, you want to kind of get used to the tasks that you're going to be doing in the hood. So perform a mock transfer of the digestion solution into the 100 ml volumetric flask. So how are you going to rinse the plugs? How are you going to rinse the digestion vessels? How are you going to insert the funnel? Which side of your body are you going to have the rinse bottles, the squirt bottles, left or right? What hands are you going to use to hold what, and kind of how you're going to go through this task? So just get a mock setup going so you can kind of get a feel for exactly what's going to happen once you start working with the digestion vessels, the transfer, and filling up your volumetric flask. So once that's done, then you want to take the clean funnels and volumetric flasks for use, line them up in a fume hood, and then bring in your clean vessels, and then slowly vent those vessels into the hood. Rinse the vessel plug with DI water. Rinse that into the vessel itself. Rinse the vessel, fill with DI water. Rinse the funnel, and then fill the flask up to the mark with DI water. Invert and swirl 6 times to sufficiently mix that solution. So to recap, you rinse your plug into your vessel, and then you dump the contents of the vessel into the volumetric flask, and then you're going to rinse that vessel and then fill up to the mark with DI water, cap and swirl. Now do that for all of the digestion vessels that you ran through the cleaning stage. Next step is we're going to look at that. So there's a lot of moving pieces to this experiment. So we have the vessels, the vessel caps, we have the volumetric flasks, you have funnels, you have the test tubes that's going to be loaded onto the instrument. So there's a lot of points for contamination. So we need to look at all those points. So set up a method on the analyzer. It doesn't have to be perfect, but it has to be well thought out so you can get an idea of the contamination levels within your digestion process. I use 2 reference points for the calibration. US FDA in EAM 4.7, they used 0 to 2.5 ppb calibration, and AOAC method used 0 to 5. So I opted for the higher calibration, not knowing how the samples that I was about to embark upon was going to react to the digestion and what levels of contamination I would see in the beverages. So once you get that set up, now you want to assess the data and repeat cleaning for any elevated levels within your digestion apparatus and volumetric flasks and test tubes. Sample preparation. So reviewed US FDA and AOAC and CEM methods for food analysis. These methods called for nitric acid, hydrogen peroxide, and hydrochloric acid, microwave power at 1600 watts, calibration matrix at 1/2 acid concentration of digest. The thought process here is that some of the acid's going to be consumed during the digest. So in order to matrix match, they opted for cutting the acid concentration in half, assuming that would be approximately equal to the levels of percent acid within the final diluted volumes of sample. And then again, within these methods, the instrument settings wouldn't apply because we're opting for cold vapor atomic absorption technique for the determination of mercury. So for a trial run, I used 5 mils of DI water into the vessel. So it's called wetting the vessel. It's always nice to have a little bit of solution in there prior to adding your sample, whether it's a dry sample or a liquid sample. If a dry sample, you'd want to put the sample in and then add a little solution on top of that to wet it before your acids. So in my case, I used DI water and then the sample, 5 mils, and for the trial run, brewed black coffee. I next added a mill of HCl, and that's to stabilize any complex, I should say, any liberated mercury during, before, during, and after the digest as well. Then 8 mils of nitric, and then 1 mil of hydrogen peroxide. 30% peroxide is what it was. And then the final dilution of all this is going to be up to 100 mils. So CAM recommends for 8 to 12 vessels, 800 watts. So I opted for a slightly more aggressive power setting on the ramp, but then a less aggressive setting on the hold portion. So the ramp time on my method, 25 minutes. I used a max power of 100 watts. Hold time at 15 minutes, 600 watts, and then the control temperature at 180 degrees C with the temp guard up to 200. Calibration matrix was 1/2 of the acids that are in the vessels, so 4% nitric, 0.5% HCl, and I didn't add any peroxide, assuming that the peroxide would be consumed, fully consumed during the digestion. My calibrations were 0, or I should say blank, 0.05, 0.2, 0.5, 1.0, 2.5, and 5.0 ppb for this experiment. The M7600 instrument settings, I adjusted these for the reduced flow or green chemistry peristaltic pump tubing setup. This was first introduced with application note 1905. Gas flows are at 100 mils per minute. My pump rate for the system was 50% with an uptake of 50 seconds. So about 5 mils per sample, and the Stannis was approximately 1.5 milliliters per minute. I should say 5 milliliters per minute on the sample at 50 seconds. Read delay was 68 seconds. I'm doing 4 integrations at 1 second each on peak height. Rinse time was 100 seconds with rinse pump set to 50%. The rinse flow is about 12 milliliters per minute, but I recycled back to the rinse reservoir, so very little is consumed. And then a baseline correction point. I only used a single front end baseline correction point. It was set at 32 to approximately 36 seconds. And then for the line, I used linear with force through blank. So the trial run, the results looked really, really good. R squared was 3 9s and a 0.9. Initial calibration verification came in at 97.4. The continuing calibration verification was at 103%. Control blank was 18 ppt, 0.018 ppb. Average sample at 0.018. Standard deviation was 0.012. And the pre-digest spike was 100%, and post-digest spike was 100%. So with that, I thought, well, it looks pretty good, but let me review the spectra. So looking at the peaks, it appears that there's a kinetics issue. There was a long tail on the coffee sample, shown here, a long tail. The control blank seems to be okay. So is it interference with peroxide or an incomplete digestion? Not really sure where to go with that, but I took a step back and went back to the drawing board. So coffee's organic. Most beverages are going to be organic in nature, especially with the added sugars for sodas, etc. So maybe it's more about the carbon bonding rather than the peroxide issue, or a little bit of both. So the next trial digestion procedure, I opted for 5 mils of DI water, 5 mils of sample, 2 mils of hydrochloric acid. Again, it's very important to get that HCl in there. First step to complex any mercury that's going to be liberated by the following additions of acid and or the microwave digestion process itself. Next, I added nitric acid, and then finally 2 mils of sulfuric acid. The thought process is here is that the sulfuric is going to break the carbon-carbon bonds within the sample and may do a better job than the peroxide. So the change in preparation worked great. R squared was 3974. My initial calibration verification was 98.4. Continuing was 103 and 105. The control bank came in at 5 ppt, 0.005 ppb, and the average of the samples minus the control blank was 0.001. So now we're basically down to the non-detect level, which was hopeful, and I drink a lot of coffee, so that's all good. Control blank corrected standard deviation at 0.0015 micrograms per liter. Pre-digest spikes came in at 102%. So the change in sample preparation improved the spectra. When reviewing the peaks, the long tail is gone. So here's the sample peak, it's gone. It comes back down to normal. And then here's the blank correct, or the control blank, so it all looks good again. And again, we are down at the trace level for this, so this is at the bottom end of detection for the system in the 1 to 5 nanogram per liter range of detection. So I decided I was going to tweak out the instrument a little bit more, still using the green chemistry pump, the smaller ID pumps, that's reducing the waste by 40%, reducing the Stannis uptake by 53%. My gas flow is at 100 mils per minute. Pump rate, I went to 70% to put a little more load into the system, but I stayed at 50 seconds. So now I'm using approximately 7 milliliters per minute sample, and Stannis is approximately 2 liters per minute. Read delay was about the same, 66 to 68 seconds. And the rinse time, I opted to keep it the same because I have overflow of the rinse station. And again, that's recycled back to the reservoir. So when you recycle the rinse, it's part of the daily maintenance is to clean that rinse bottle and refill with fresh rinse so it doesn't become contaminated for future runs. But it does save a lot of solutions, so you can calculate how much rinse you're going to use for a run and make that volume plus a little bit overage, and then you're really good to go, so you don't waste a lot of solution. The goal here is to minimize stannous chloride uptake and waste production within the system as well. And again, linear and force through blank was my mode of detection. So the method scope applies to common beverages consumed by humans. The analysis principles are: a sample of known volume is pre-treated with HCl, nitric, and sulfuric. That pre-treated solution is going to be microwave digested at 40 minutes. Extraction solution is then diluted to 100 mils, and then an aliquot of that diluted solution is going to be analyzed by chemical reduction and cold vapor atomic absorption. Quantification of the mercury is calculated back to the original beverage volume and reported. The reagents, chemicals, and solutions, so you need a source of DI water, ACS grade hydrochloric, nitric, and sulfuric, and then some Contrex acid cleaner. This is what I use in the lab, or similar, and then a cold vapor atomic absorption instrument, and any specific chemicals to that instrument, such as stannous chloride, is going to be needed for this method. So in this case, the sample prep, 5 mils of DI water, 5 mils of sample, 2 mils of hydrochloric. Again, that's that complex or preservation mode. And then 2 mils of nitric, 2 mils of nitric, 2 mils of nitric, 2 mils of nitric, and then sulfuric acid, and then cap and digest. So if no reaction occurs after 10 minutes of the first addition of any of the acid, including the nitric, then you can go ahead and add the second one, monitor, and finally the total volume of 8 mils of nitric and then 2 mils of sulfuric. So I do highly suggest try a mock trial of any beverage you're going to analyze in a 50 ml test tube. Mock it up and add your reagents and your acids to see what's going to happen, because some of them can be kind of a violent type reaction, and you don't want any effervescence or any foaming to come out of your microwave vessel. So do a mock reaction, and then once you know each individual beverage, then you can tailor the addition of the nitric acid to that beverage. For example, if you don't need 2 mils of nitric in small additions, if it doesn't show any reaction or adverse reaction to those additions, you can go ahead and add 8 mils at one time and greatly speed up those steps. For the instrument settings, probe depth with 150 millimeters. My pump rate on the auto sample was 50%. Uptake time for the sampling was 50 seconds. Rinse time was 100 seconds. Gas flow was 100 milliliters per minute. As I mentioned earlier, the pump speed was 70. My read delay time was approximately 67, 1 replicate times 4. Baseline correction was 24 to 28. Calibration is linear. I use quantitation mode of peak height. This system gives you the option of doing peak area and or peak height. Just depends on how fast you want to run it. And then my calibrations, again, were 7 calibrations, PPB level and linear. So the analytical runs I performed, calibration, ICV, CCV, CCB, CCB, 7 samples, pre-digest spike, post-digest spike, tap water, and control blank. So I ran 10 samples within each digestion run. Brewed coffee, orange juice, red wine, soda pop, 1% milk, and brewed tea. The orange juice didn't present any issues with the 5 ml sample during acid digestion, and it flew through that process. Here's an example of the control screen for the microwave. It shows the ramp up time and then the hold temperature, and then the individual temperatures within each vessel as well. And again, there was no issues with that. Red wine, however, did pose a challenge. When I added the 2 mils of hydrochloric and 8 mils of nitric, without delay, it was extremely effervescent and created quite a mess over here. So it flowed out of the digestion vessels, and so here's the control blank and the DI water, and so there was a pretty good mess within the hood. So I had to clean that up, and then looking at that, that's what created the addition of 2 mils at a time, and the necessity for looking at individual beverages by doing a mock digest of the system. So here's depiction of that mock digest, and then this is the wine. Still a little bit of effervescence within it, but I was able to contain it with the slow additions of the acid. Also, another trick is to ensure that you add your acidic additions down the side of the vessel rather than straight into the middle, hitting the solution itself. So bring it down the side, kind of try to slow that reaction as well. The next 3 digests didn't present any problems at all. They were prepared for the microwave in a few minutes. So soda pop, milk, and brewed tea. During my trial run, the milk, after the addition of the acid, it kind of resembled orange juice. I thought that was really, really interesting of how it looked like orange juice. But again, that was done in a few minutes and off to the microwave. So some of the analytical experimental variables within this method, so digestion vessels, cleaning and validation, volumetric vessels, cleaning and validation, funnel cleaning and validation, sample tube cleaning and validation. So there's a lot of pieces to this process where contamination can be introduced into the system. So you really need to use the best GLP possible. For this application, it's prudent to empirically test the sample's reaction and timing to the acid additions. The results, all calibration line correlations were well within acceptable range. So all 3 nines greater, even 4 nines. All ICV recoveries are well within the plus or minus 5%. So 98, 97, 96. 97, 99, and 99. Actually, this is almost 100%. Blank corrected values were all less than 5 ppt. So here were 01, 001, 002, and so forth. So basically non-detects within the system. The method digest, so standard deviation at 95% student t-value distribution of n equals 6. So that's what these values are right here. So it's the standard deviation of the 7 digested samples. So we have 0.0037. The worst one was 0.008. So again, less than 10 ppt for an MDL within the digest itself. Pre-digest spikes seem to tell the story that there's no analytical loss in the system. So this is a 0.05 50 ppt spike within the system run through the entire process. So everyone is almost 100%. There's also a post-digest spike that I didn't show here. That's 0.048. It was 0.5 mils of a 1 ppb into 10.5. The average percent recovery on that was about 96%. So overall, the results look really, really good. I opted to perform a complete CFR 4136 Appendix B Rev 1 MDL study. So that's from front to back through the whole system. A microwave digest, the vessels, the filters, the volumetric flask, everything. I prefer the original MDL guidance rather than Rev 2, so that's why I did the Rev 1 guidance. My samples were 5 ppt and 3 ppt. They were processed through the entire procedure, which resulted in a 0.26 ppt or 0.0026 microgram per liter MDL as shown here. So here's the 5 ppt and here's the 3 ppt with the average of 3.8, 5.9. So really, really good results through that whole process. Now for a limit of quantitation, so some people do 2 to 5. I prefer MDL times 3. So that's going to give me my lower limit of quantitation at less than 9 ppt or 0.009 microgram per liter for this entire system. So with that, the data set in hand, and using my new calculated LLQ, calculations of all the digested MDL data fall within that. So when I look at this, all that data is within that calculated MDL. But since we're using 5 mils of sample into 100 mils, that's a 20x dilution. Then we should report at 180 ppb. So 0.009 MDL, HG in the coffee, orange juice, red wine, soda, milk, and brewed tea. So we're going to be less than 180 ppt or 0.01 microgram per liter within each of those beverages. So in conclusion, the microwave digestion and analysis of the 6 beverages tested. It wasn't all that difficult once I figured out some of the kinks and worked out the mock digest of each beverage that I was trying to perform through the entire system. Both digestion and analysis can be completed in one day. The challenge is the labor-intensive cleaning effort that's needed between sample sets. So there's a lot of GLP that needs to go into this to ensure that you keep that contamination down to a minimum. Pre-digestion spike recoveries were very good amongst all the beverages tested. They range from 98 to 102%. So there's many fluid pieces, and again, the strict GLP must be deployed to get meaningful data within the system. Conclusions: the MDL at 2.6 ppt shows that the complete system capability is better than most systems when working in the ultra trace range. And again, this was very complex. There's a lot of moving pieces here. By subjecting the analyzer to the modified gas flow, pumping rate, uptake rates, it's very possible that we could achieve a much lower MDL. So if we drop that calibration down from 0 to 0.1 ppb or even 0.2 ppb, this instrument's very capable of achieving those methods. Then we could have probably MDLs of much less than that, less than 1 ppt. So then when we run that dilution, that's going to give us less than 60 nanograms per liter for those lower MDLs, if it's less than 3. Method summary: extraction methods yield a final average result of less than 180 ppt. The 7600 coupled with the microwave used demonstrated its capabilities to report values in the trace HG ranges for a complex system, start to finish. Performing the method was relatively straightforward, but again, I have to stress the cleaning process of all laboratory apparatus must be the most important for the data to be relevant. Some of the references: CEM Corporation, general guidelines to assist in microwave digestion, their manual for their system, the U.S. Food and Drug Administration methodology for environmental analysis manual, section 4.7. And with that, I'll conclude today's presentation. And again, I would like to thank you all for listening to the presentation, and happy analysis.